René, hello, welcome.
Good afternoon, Dodo, and to all our participants.
We'll be giving everybody 2 more minutes to log in, and then we'll be starting this
Yep,
quick
excellent.
15-minute session. All right, René, have you gotten your water or coffee?
Yep, I'm all set. Thank you.
Perfect, me too. Some
Hope you all
water.
have the coffee and lunch good to go.
Yep, so then we can start. Welcome everybody to today's session on an introduction to measuring electric power during transients. Yesterday we talked about NVH and the day before about torque ripple. My name is Dodo Husmann. I am your host for today. And with us is René, our speaker for this topic. Hi, René.
Good afternoon, all.
We are going to record this session and send the recording and slides to you afterwards. If you're having any questions, please feel free to use the chat function or the Q&A field, and then we'll answer them afterwards. You can also send an email to us if you don't have any questions at this point in time. And just making you aware of our LinkedIn community for electric power testing. If you want to be part of it, I have put the link to that group in the chat function, and I'd be happy if you could join the community. Handing over to René and wishing everybody lots of fun.
Thank you, Dodo. Thanks for that introduction, and thanks again for hosting this event. Welcome to you all. So today's session, the last of the 3 sessions of this week, will be the introduction to measuring electrical power during transients, and we will start this one with a fun but very applicable little trivia that I borrowed of one of our colleagues, which is what 2 things do lightning and inverters have in common? In fact, it's something quite relevant to this topic of today, measuring transients, and we will get to the answer by the end of this session. So let's start with today's agenda, transient testing introduction. So basically, why do we bother with transient testing in power measurements? Followed by the challenges. Why is this challenging? Why is it potentially difficult? And why is transient power different from any steady state power? This will be followed by the HPK value for transient power testing, and we will close the session with a little test example and the answer to our trivia. So, transient testing introduction. Well, if we really want to understand the true energy usage of a vehicle, we need dynamic testing. So dry cycle tests, like we see here on the right side, are typically defined by governments and authorities and used as a common indicator. So we have one similar test routine which we can use to compare different vehicles, different motors, for example, to each other. And those test routines are typically defined as speed over time. They are quite useful in benchmarking and validation. And it basically shows you how many distance you can get out of one battery charge, for example. It's a way of fuel economy. Also, research and development departments typically use these either as a full cycle or just the portions they are interested in to look into how to optimize the drivetrain. And the key takeaway from this picture is it's a constantly changing frequency. So it's never a machine running at a steady state. So these tests are used to characterize our final product. That's one thing. It's also used to calibrate or to match our motor and inverter together, as we want those motors, inverters, drivetrains to be as efficient as possible in the specific drive cycle. Another topic in such testing is driver experience. So when we drive our vehicle and we want to accelerate or we want to drive at a steady speed, we do want it to be smooth. We do not want to be jerked around by acceleration and deacceleration all the time. Except, for example, if we have maybe like a sports car, we might like this acceleration to be a bit more aggressive, but in general, it needs to be smooth. It's also a way of comparing supplier parts, but also for comparing with competition, so benchmarking. And this can be done on a component level, like here we see in a motor dyno. It can also be done on a full scale level, like we see here, for example, in a chassis dyno. And those are also the typical ways to do those drive cycle testings. But in fact, as we know the testing conditions, we can already start testing on a component level, even without having a full vehicle developed. Another way of testing which is being used is in fact road testing. Have an actual driver, instrument the vehicle, drive it around, and really investigate how this specific driver is using the vehicle. So let's say the 18-year-old compared to a grandpa driving, it will definitely have a different energy usage for this vehicle. And that is what in the end it all comes down to. Vehicle energy usage and how to optimize this. So what are the challenges we see here in transient power testing? Well, as mentioned, there is no steady state frequency as our vehicle speed is constantly changing. That's a given. Our traditional power analyzers, we use a PLL to track the fundamental frequency. They require a more or less fixed frequency or at least some time to adapt to the frequency. Another topic we see here, and we come back to that later on when we discuss the trivia, is traditional recorders cannot measure PWM due to the steep switching behavior. It's not only the speed that's changing, we have constantly changing states, transient caused by clutches clutching in and out, like we see here, for example, in this transmission. Multiple machines which might be interacting with one another, temperature changes, and also road surface. Think about ice, for example. If your wheel hits a slab of ice, it will speed up. If you hit a pothole, you will have this steep transient in the load of your electrical motor. So why is this difficult to measure? As we could consider, for example, if we take this changing frequency here, and if you want to do this with a traditional power analyzer, okay, we mentioned we cannot do that as the frequency changes too rapidly for the PLL to track. Still, we could consider analyzing our drivetrain with our traditional power analyzer at a multitude of different torque and speed set points. So we get a bit of a fingerprint of the drive, and we still could compute more or less what our efficiency would be during this change of state by using all those individual measured set points. In the end, transient power is a bit different. It should not be regarded as a steady state. So why is this different? Let's look at this example of a motor starting up. So when we start up this motor, we have a big inrush of current, and this inrush of current results in a big reactive power spike. This reactive power spike on its turn results in heating in the machine. It results in losses. So this is additional losses during change of state. In this case, we go from 0 to a certain speed. This square wave you see here, by the way, it's something we will discuss later on. So basically, any change of state has a similar behavior. Any change of frequency, any change of speed will result in reactive power and additional losses. So this highlights why dynamic power measurements are needed to actually understand our efficiency during true usage of a vehicle when it's subjected to dynamic loading conditions. So what is the value HBK can offer here? And there we will go to in a bit of background detail why we see this square wave here, as this is in fact a picture that was made with one of our systems. So the eDrive value in this case of the HBM eDrive testing solution is the fact we can do those dynamic power measurements. How we do this, we will explain in the next few slides. Another big topic here is properly time aligning all your signals, as when you want to calculate efficiency, so energy transfer from one state to the other, you need to make sure your measurements are properly aligned in time in order to avoid calculation errors. This time alignment and the dynamic possibilities allow for accurate energy and power measurements. Additional benefit of the system is its future-proofing your testing capabilities. So one might start with a system with just 2 slots used for a 3-phase machine. And if you, for example, later on need to switch to more phase machine, multi-level inverters, add setups which measure vibrations as well, you name it, it's just a matter of slotting in additional boards to this mainframe. And also those mainframes are available in various sizes. So we have smaller ones like the 2-slot mainframe here, but we also have bigger mainframes like a 16-slot. So this is a way of future-proofing your testing capabilities. Additionally, it provides for auditable testing. So all the data is recorded for review, but not only the data is available for review, but also the calculations, like the formulas used to get to your results, are available for review. So we do not tell you only the result, we also tell you how we get there. It also simplifies the measurement chain, as we can supply sensors, acquisition, and software. So here we see the example of the torque transducer, which you can also consider current transducers, accelerometers, you name it, the acquisition system itself, and the suite of software. So here we see the real-time display used during any power measurements. And what we see here is the post-process analysis, like a motor mapping being done in the same suite of software. So how do we do this dynamic power measurement? To enable us to do a proper dynamic power measurement, we need to have something which is called cycle detection. So to compute the power results, the cycles of the signals are needed. So if we look at this example here, this is a current signal, it's noisy. So a simple zero crossing detection is not sufficient to measure those half cycles of the current. Those half cycles are where we are interested at, as that's the most dynamic power calculation we can do. So we designed a clever algorithm which detects those cycles up to a half cycle level of the signals, and we run those in DSPs on the boards. So that's another important detail to the system. Each power board has its own DSPs running all the calculations, so the calculation power of the system scales together with the expansion of the system. So this allows us to calculate our RMS values, powers, efficiencies, and any advanced calculations on a cycle basis. So the most dynamic way is using the half cycle. But if you are more interested in a high accuracy, a low measurement uncertainty in a steady state, one could in fact even average those cycles to get to a lower measurement uncertainty. Even better, one could do both at the same time. So at the same time, you can have the lower bandwidth, high accuracy results, as well as the high bandwidth with the basic accuracy. So how does this look like? Let's look at an example where we do a dynamic test with a cycle detector. So in fact, this test was done by one of my colleagues who instrumented an electrical scooter with one of our systems. And what you see here, let's go through the properties of the signal. So we see here the scooter being kicked. This is a feature of the vehicle itself. You need to kick it before it starts motoring. So we see some power being generated, in fact, into the battery. And then we see it start speeding up. So we have here the currents, voltages, and also the power. So the apparent power, reactive power, and the real power. And we see this is not exactly linear. There are some dips, there are some hills in it, and this is caused by the environment conditions. So he might be driving uphill, he might be hitting a gust of wind. But more interestingly is this area where we see when the vehicle speed tops out, either by current limitation or by speed limitation, we see again this overshoot in the apparent and the reactive power. So this means additional losses. And by optimizing the motor control those losses could be reduced, in fact. So we see here there is an opportunity in this specific vehicle to get some more range out of one battery charge. So far we have learned drive cycles and in-vehicle testing require dynamic power analysis. Cycle detection allows for this dynamic measurement. Dynamic testing lets us users characterize real-world scenarios. And it also enables us, as we see here, to reverse engineer any equipment and see how it behaves in specific conditions. So let's go into a little test example of a full drive cycle. This is again the same electrical scooter, and you can do such a drive cycle on a dyno, like a motor dyno, on a chassis dyno, like a full vehicle, or just by doing vehicle runs. And this is what has been done in this case. My colleague has just been driving the scooter around the park, and here we see the measurements. Again, voltages, current, the frequency of the electrical signal, which is then equal to the cycle frequency, power, and finally, the total energy consumption from a dynamic load situation of a certain drive cycle. And this is really needed to understand the used energy in specific scenarios. So we require dynamic power tracking and a cycle detection to follow this fundamental frequency. Which brings us to the conclusion. eDrive is a system effective in measuring vehicle power flow, can be used to measure vehicle energy on a dyno, chassis dyno, or in a vehicle. Cycle detection allows us for accurate and dynamic power measurements, and the raw data ensures that calculations of power and energy are correct and auditable as well, together with the auditable formulas. So that brings us to the final point, the trivia we had in the opening statement of this presentation. So what are the two things in common between lightning and inverters? One point is they have really fast electrical transients, where lightning can reach 30 microseconds and IGBTs, the components used for the switching in the inverters, down to 50 nanoseconds. And both are tested with the HPM power testing products. Important point to mention here, if we do typical power measurements, we just limit ourselves to 2 megasample, as that's plenty to track the fundamental and plenty to measure our electrical power and the efficiencies. Now, if we really want to go into this transient behavior, really want to look into the electrical switching of the inverter itself, that goes beyond power measurement. Still, we do this with the same system. As mentioned, it's modular, so we can slot in additional acquisition boards. And for this type of testing, we typically use the higher sample range, which go up to 100 or even 250 megasamples a second, which is way higher than what we require for the typical power measurement. So that brings us to the end of this session. My name is René Bastiaansen. Feel free to connect to me on LinkedIn if you would like to have a personal discussion or have some questions. You can also visit our webpage. This link brings you directly into the specific electrical power testing area, or you can use your smartphone to scan this QR code and you will end up in that same page. So let's see, Dodo, did we get any questions during the session?
Thank you, René, first of all, for this great session. Again, so much information in a very condensed time frame. We have not received any questions so far, so please feel free to use the chat or Q&A field. Again, if you don't have any questions at this point in time, you can also get in touch via LinkedIn with René or in the EPT community group. We'll send the recording and slides to you afterwards. And if you want to register for part 2 that goes more into detail, we'll send you an invitation to that via email. So look out for that. Thank you, René. Thank you for everybody who participated today. And we'll just stay online for another minute to give you the chance to ask questions.
Dodo. So as mentioned, feel free to drop any questions into the chat. And otherwise, if you would like to take it offline, feel free to contact us directly, either through the website or LinkedIn.
René, you just explained it so well that every question has been answered. That's what we want, right?
Yep, most definitely. I hope it has been a useful set of information. It's always a nice challenge to bring a subject in this condensed time frame, but I I must say Mitch did an excellent job here, one of our colleagues, to prepare those materials.
Absolutely.
So credits to him, most definitely.
Let's see. There's actually a question, Renee. Could you quickly recap why cycle counting is needed for accuracy?
Well, let's get back to that specific slide. So for accuracy, the cycle detection is mainly important for the dynamic measurement. But if you want to get more accurate, a very convenient way and proven way to get more accurate readings in a stable situation, that's one point that I must stress, is averaging. So each half cycle, we have a power measurement result, and the next half cycle, and the next half cycle, and the next half cycle. So if you take a multitude of those and we average, that is one mathematical way to reduce measurement uncertainty. It's just statistical. So that's why we mentioned that over here. So we can either take the dynamic signal, which is one single measurement, or we can take the statistically improved result, which is the average of multiple. But then you lose some of your dynamics. Good thing is the system, having its DSPs, is capable of doing both. So we can give results with a high bandwidth, so with the update rate of 1/2 cycle, while at the same time calculating a sliding average of a multitude of cycles. I hope that explains the question a bit. Interesting subject, definitely. Measurement uncertainty. I think we should do one on that as well. And definitely, if you have specific questions about that subject, feel free to reach out.
Thank you, Renee, for answering that question. And yes, we will send the PowerPoint slide to everybody via email. All right, then let's close the session and see you all in some upcoming sessions. Just keep an eye out on the hvm.com website for future webinars and Lunch and Learns. Have a great day, everybody. Renee,
thank you.
See you later.
Okay, have a great day. Take care all. Bye-bye.
Bye.